Okay, Jacob.
Here.
Jacob Iverson. And Brianna. And Abel. Okay, so this is trigonometry, and for those whose names I called, you lucky few, you guys are in algebra and trigonometry. So you guys are really lucky, right? So either you had algebra in the morning and then you come to trig, or you're coming to trig and you have algebra tonight. All right, now be aware you guys are in for quite the semester. Okay, so 1450, all right, is a 6-credit class actually encompassed in a 7-credit class, all right, in which basically you're taking 2 math classes simultaneously. Okay, is that what you're aware of what you signed up for? Okay, I want nods from all 3 of you. All right, because all right, that is quite the class, and that's all ideally. Are you guys all headed to calculus?
Yes.
Right, it's all to get you caught up to start calculus in the fall or summer since you guys are the overachiever type anyway. Okay, so I just want to make it clear to you guys that you really need to stay on top of your stuff. All right, you are going to have basically you have 2 instructors, 2 different classes. All right, and it is an absolute ton of work, but super rewarding. All right, I don't want to intimidate you on the bad end. All right, so I just wanted to make that part clear. All right. All right, this is the trig part. All right, and ideally, is everyone in here going to calculus, or is some of you guys, is this as far as you need to go? Is everyone going to calculus? Yeah? Calculus? All right, okay, excellent. All right. So that means, all right, that we're taking an approach, all right, that is the proper approach. So I am Bo. All right, email is the best way to get in contact with me. Phone is by far the worst way. Canvas, that email is fine too. There's my office hours, as well as I do time in the Student Success Center. And the Student Success Center, we try and have that open like 9 to 6 Monday through Thursday, and like 9 to 3 on Friday. And it's open 12 to 3 on Sundays. So we try and have that open a lot for if you need additional help. But I was like, feel free to email me, feel free to come see me. I was like, definitely want to help you guys out. You guys are in some of the highest math that we're offering. All right, so we're definitely you're starting to get up there, what we finally call you're in math. All right. So ways to contact me, and definitely if you need assistance and you don't want to come see me, or you're just like, oh, like I have a question and he's not in his office, like go to the Student Success Center. Go definitely check it out. I hate it when it's like midterm and I'm like, oh, have you gone to Student Success Center? What's that? All right, so it's this nice free assistance tool. Take advantage. All right, so for our text, all right, we're using a pre-calc book, but really we're using Pearson MyLab and Mastery. All right, ideally you're familiar with this. If not, there's a nice, beautiful walkthrough on Canvas of how to sign up for it. And basically, that's how we complete our home funds. Also notice, right immediately, I said home fun, not homework. In this class, more than most others, it is the definition of fun. All right, you shouldn't be this far in math and still not like math. I was like, if you really did have a displeasure of math still, time to rethink your life, right? I was like, at this point, you need to start liking math. All right, so I like to call it what it is, home fun. All right, but anyway, so your assignments are located in Pearson MyLab and Mastering. Course description, purpose, all kinds of stuff. Read that later. The grading, pretty simple with the grading. 15% activities, 20% is the home funds, and 65% are quizzes and exams. All right, this is a pretty test-heavy class. There's no projects, there's no anything else. I was like, we basically solve problems in lecture, then we have some time for activities, as much as we can. We don't have a ton. All right, and then you go home and you do more problems, and you come in and do the test and do more problems. All right, problems. All right, that's basically what Trig is. Now, be aware that I'm pretty lax on this. It is optional. You don't like doing the activities, don't do them. You don't want to do the home funds, don't do them. Your grading scheme, all right, can become 100% exam-based. All right, if you are a good test taker, terrific. All right, the class is not designed that way because ideally, if you're not doing the home funds and you're not doing the activities, how do you think you're doing on the tests? Probably not great. But if you're doing the home funds and you're doing the activities, that encompasses 35% of your grade. And let's say we're getting near 100%. Should be pretty easy to get that value. First math question, 35% times 100% is? Let's back up a step. How do you multiply percentages? Not rhetorical. No one knows how you deal with a percentage?
Wouldn't it be 0.35 times 1?
Yeah, 0.35 times 1, which is
0.35.
0.35, aka, back to percentage, 35%. We all right? I was like, but this is math. All right, so that leaves 65%. In order to get a C in the class, what percentage do we need? 70%. This one should be easier. 35 plus what number makes 70? 35. So how do I work this backwards to fill this guy in?
Take the 65 and move over to the other side.
Right, yeah, so this says X, what's the quick? So what do what to what?
Divide 65 by both sides.
Yes, so AKA, what divided by what?
0.35 divided by 0.65.
Right, and in this case, I can just do 35 over 65 since they're both decimals. All right, which gives us 54%. So notice what this means. All right, if you're doing your home funds and activities, All right, and home funds, Pearson, MyLab, and Mastering, you can do those problems over and over and over and over again until you get it correct. It has instant feedback. It's a really, really nice software. It's really helpful for the learning. It's a little persnickety, but that's life. The activities, basically, we do them in class. I have the answers on them. I give them the kind of the once over, and I have like a graded problem, but really, it's pretty easy to get 100% on that as well. As well as, I mean, basically, you'd be like, hey, before you turn it in, you'd be like, hey, is this 100%? All right. So that means that basically, if I'm doing all this stuff, what letter grade am I getting on the tests? An F. I'm failing all the tests, and yet somehow I passed the class. All right? Math is about doing the work outside. All right? The tests are a snapshot. Do we have bad days and you didn't do so great on a test? Yeah. Ideally, this is an average too. So if you have consistent bad days where you're not even getting half the answers right, that's a more fundamental issue. But hey, on average, ideally, being able to get a 54%, all right, on all the tests should be very, very reasonable. All right, so this class is designed to be passed, all right, when you do the stuff outside, all right? Because between the lecture, the activities, and the home funds, if you're doing all that, regardless of how hard you're trying, you're going to be accidentally learning, all right? And that's really the goal. But, all right, so it is choice. All right, multiple places on the syllabus, I say home funds and activities are optional. And this is what I mean, right? There is no late, no exceptions for home fund and activities. If you don't turn them in by the due date, all right, and due time, which is the start of class 1 p.m., all right? So on whatever specified day, we'll see the calendar in a minute, all right? That grade doesn't get a 0, it gets grouped onto the corresponding test. All right, so basically, let's say this first set of stuff, which is chapter 5, part 1. I don't do the activities, I don't do the home fund. Well, like now that test is weighted more heavily. All right, and that's what that means. Now, it's the same math. What if I have 100% of my quiz and exam grade based on a test? What percent of the test do I need to have correct to get a C?
70.
70. Well, that's very, very reasonable still. 70%. Times 100% makes it 70%. All right, but again, if you don't do anything else and you do it this way, it's a lot harder to get that 70% since you have seen almost none of the problems. Now, I've had lots of people try this method in almost 20 years of teaching. I've had 5 out of thousands of successes. 5. All right, don't do this approach. Do this one. But it's still your choice. All right, as for late, so like I said, activities, home funds, no late. But for your exam, do your best. Look at the calendar, see when the exam dates are. If you have the exam date, and you're gonna miss, let me know. We'll work out a time, all right? We have particular times that we get you set up. But basically, I have to be immediately contacted if you're missing the exam date. All right, and we'll figure it out because I'm a super fast grader. And if we have the exam on Tuesday, I'm passing the exams back on Thursday. And if I'm passing the exams back, and you're like, oh, I didn't take it. Well, you have 0 now. All right, so I was like, I must be contacted and we will work something out. So that way I'll be like, oh, I'm not going to pass the exams back on Thursday, right? Because you needed an extra day, all right? Which is absolutely fine. Oh, I couldn't take it till Friday. I get it, all right? But just need to be contacted. All right, so attendance, stuff to read. All right, so turn-in procedure. So the activities, all right, basically I have a folder, all right, turn-in folder. I put it out and basically you can turn in the activities, all right, you can turn them in daily, you can wait until they're due, it's absolutely fine, it's up to you, however you want to submit those. Also, they're available to be turned in online. All right, so you use Cam Scanner, and I have a little Cam Scanner activity if you're unfamiliar with it. So that way, oh, you're gonna miss the exam. Well, you can still turn your activities in via online, which is absolutely fine. If you're turning them in on paper, legibly write your first, last name, title of the assignment. Right? If you're turning them in via Canvas, it links to your account, so it's not a big deal. So yeah, so again, you should be able to always turn them in, and absolute worst case possibility, you can sit there and take pictures with your phone and then email them to me, all right? Or use Canvas or submit a paper. This is the absolute last option. I just want to give you guys options. All right, home funds, my math lab online. And so here's the other thing, like I was saying, my Pearson can be persnickety. Oh, you didn't have it in quite the right form, your parentheses are wrong, or I mean, that might be a more fundamental issue, but if it was something persnickety, I have what I call the good enough assignment fulfillment. If you get a 93% on your home fund, I consider that full credit. All right, especially, you know, some of them have parts A, B, C, and you get down to C and you missed it and you're like, oh, come on. Like, I don't want to redo that whole problem. So move on, look at all the problems. When you get up to a 93%, that's full credit. No late. Oh, the lecture notes. So I printed the lecture notes and the first activity for you. All right, this is the first and last day I print that stuff for you. All right, it's all on Canvas. You should be able to print it and get it all for yourself. All right, don't turn in your lecture notes. They are for you. All right, keep those, hang them on your fridge, sleep with them, right? They are, all right, for you to study. And then just as a note, cell phones. So I don't allow cell phones during tests. However, activities, home funds, feel free. And I highly recommend, if you don't have it already, download the Desmos app. All right, does everyone know what Desmos is? All right, Desmos is just a fantastic graphing and little solver. It can be very, very helpful for a variety of uses, algebra review, graphing, things like that. Download it, use it. All right, but I don't allow it during tests because there's just too many math solvers out there. And I'm trying to test your specific knowledge, not your ability to use your cell phone. All right, so yeah, don't skip class, check Canvas. Oh, and every test you're allowed an 8.5 by 11 cheat sheet. All right, so you don't have to memorize anything, which actually reminds me, the best cheat sheet to put on there. And then get 93% or higher on all your home funds. All right, so here's our basically, and I have our calendar pretty well laid out. All right, there might be some adjustments, keep an eye on Canvas, but I plan to stick to this, primarily this schedule, right? So you can already see when things are due, all right? And actually this, in your syllabus, you see, it says cam scanner activity due here as well, right? So the first due date, which is the course info quiz, which is an easy online Canvas quiz, get in there, start this value, that's part of this, start this at 100%. All right, the cam scanner is part of this grade, start that one at 100%, all right? And so we start both those at 100%. The cam scanner is activity is due, and the course info quiz. Now, be aware, you don't do either of those. This is the only things I don't count against you because they're so easy that like it's auto 100%. But if you don't do them, I don't want them to actually hurt your grade. They're only meant to help. But it gets you familiar with a few things. And then notice that our actual first material due date is the 8th here. All right, so the part 1 activities, all right, the part 1 home fun, and we have the part 1 quiz. All right, that's all we do on a quiz day. All right, we take the quiz, all right, you turn in all the activities and stuff, and the home fun is online, so that's all done. I used to have those due dates at midnight, but the problem is people would they'd finish their quiz and then they'd immediately open their laptop and start doing the home fun, and it drove me insane. Because you're supposed to do it to prepare. And then they would be like, oh, I don't understand why I failed the quiz. Boy, sure would have been helpful had I done the home fun before. Yes, exactly. So I don't give you a choice anymore. Stuff is due at 1 p.m., which is the start of class. And again, so ideally, again, if you miss this date, you need to have it completed, but I need to be contacted by this date. If you need longer than from here to here, all right, we need to work something out. All right, and so then again, I have basically the course schedule laid out there. So along those lines, all right, so in Canvas, so here's that walkthrough I was talking about of how to sign up, all right, for Pearson MyLab and Mastering. It links you to the site, all right? If you're not doing it on an iPad, you can actually see it says Pearson MyLab and Mastering over here, right? And you can, it can take you into the course and it links your Pearson account. It has an ebook, very, very nice. All right, so little fact and bio, syllabus. There's a link to the course info quiz. There's a link to the cam scanner activity. And this right here, all right, so I was talking about using a cheat sheet. This, all right, is basically this is a page from a calc book. All right, this is like the appendix of a calc book. All right, and this has basically everything we're going to cover in this course. This is probably a good place to start with your Trig cheat sheet. All right, this gives you half a page and you can write all kinds of examples and whatever you want on the back. All right, but this, all right, is basically every formula that we're going to cover in all of Trig. All right, and so that's just a good place to start. Oh, and there's the MyLab and Mastering. It'll take you to the site and stuff. Okay, so yeah, so I have announcements. Again, keep an eye on that. Module syllabus. And then, okay, so then every day basically lays out. All right, so what I did today is I printed the first, I didn't print the whole thing. I just printed the first, I don't know, 5-10 pages of this. All right, so we're going to be doing this the next several days. So make sure you get in there and print the rest of it. I did print the entire first activity, but there's also a second one. Okay, so again, today is the first and last day I'm going to print you those lectures. All right, but get in there, print it. It's designed like you see the spaces in there. It's designed that you print that and bring that. But somehow everyone always wants to just look at it on their phone and then they write on binder paper and then they flip it. The problem is when you write it all on binder paper, it just all gets squished in and you don't know how this problem related to this part of the lecture. It is just much, much better to print those lectures and bring those, and then we fill it in appropriately. But the choice is yours. I just wanted to give that heads up. All right, and then basically, all right, so you see that every section basically breaks down the same. There's lecture, activities, home fun, and a quiz. And basically we just rinse and repeat through all these interesting topics of Trig. All right. Any questions, concerns? Okay, all right. Attendance is not part of your grade, but for bookkeeping, all right, I want to do this the first few weeks, and so I get your names. Okay, all right, so I already forgot. Abel, that was you, Abel. All right, and if I butcher your first name, please correct me and tell me a nickname. If I butcher your last name, that's life. All right, Jacob.
Here.
You go by Jacob? Okay. Brianna. Okay, what is it? Brianna, okay. All right, Macy Bender. Macy. All right, Shannon, contact me. Jada, contact me. Brandon. Charlene. And Gayleen. No nicknames? No? Oh, goodness. Sorry, first. All right, and also, so I love writing on whiteboards. However, all right, we have some people Zooming, and if you ever miss, I'm gonna try and stick as best as I can to the iPad. So, all right, for those who are Zooming, and if you ever need to miss, but you still wanna Zoom, please feel free to join via Zoom. Additionally, all right, I'm recording all these lectures so that way I can post them later as well. Now I'm kind of bad at like getting them up, so I'm at least 1, 2, I'll never try and be 3 classes behind, okay? So, but if you're ever like, oh, I missed that lecture, and I'll be like, go to the video and then just be like, Bo, you haven't posted it yet, and I'll get on there, I'll post it, okay? All right, think that's everything. Any questions, concerns? We super excited? Well, now I'm curious, so everyone's gone to calculus, so what are our majors? Now I wanna know. Computer science.
I'm pre-med and business.
Pre-med and business. I was like, are you sure you need calculus?
For pre-med, yeah.
Okay, for the pre-med portion, so just Calc 1 then?
Yep.
Like, okay, I guess, like, I know some, like, pre-pharmacy has it. I was like, I guess some pre-meds like Calc 1, maybe Calc 2, probably,
See, most medical schools only require Calc.
just Calc 1, okay. All right, Brianna.
Engineering.
Oh, excellent, engineering, love it. All right, Charlene,
And biology.
biology, okay, so yeah, Calc 1, maybe Calc 2. All right, Jacob,
Science.
computer science, all right, I've got
Computer science.
Brandon, computer science, Galen, and your math, yeah. All right. Okay, all right, excellent. I was like, okay, 'cause computer science, which is basically engineering, I mean. So, okay, so engineering, computer science, so you guys, I mean, you guys are going at least Calc 2, if not higher. I was like, do you know what your math requirement is?
I'm not entirely sure. I'd have to.
I was like, it's at least Calc 2, might be a lot more. So actually, computer science was my focus, all right? I did programming for years. All my computer science classes, you know who they were taught by? Math people, because computer science is still a really new major. All the computer scientists all had math degrees, because I was like, they were the first people who did computer science. So pretty sure you guys need to go far in math. And I know you have 2 years. So engineering solidly. Okay, all right, where are we? All right, so let's get to the good stuff. All right, so trigonometric functions. So before we start talking about trig identities and all that stuff, all right, we need to actually go over, all right, what creates an angle. All right, and it all starts with a ray. All right, that is a half line, basically. You have a starting point, an initial point, all right, and an end point. We have some initial point, it goes out, and then it can extend forever. In order to create, all right, an angle, we then need 2 rays. All right, one we call the starting or initial side, the other we call the terminal side, the end side. All right, all right, and all angles go just like the quadrants. All right, they go counterclockwise, right? So when we look at the general Cartesian plane, we know this is quadrant 1. Where's quadrant 2?
To the left,
Yeah, it's over here. And then quadrant 3?
down below to the left.
And lastly, quadrant 4. All right, so, all right, it's because angles start here and they go this direction. So, just a few examples. And we like to label our angles with Greek letters. All right, so alpha is a very common one. In this case, alpha is positive. Actually, let's indicate it starts there. I can also go the other direction, and let's call this guy beta. And in this case, beta, all right, is negative. So alpha is positive. And I can also pass through my points as well. And lastly, let's call this one theta. In this case, theta is positive. All right, and in this case, theta is large. All right, so just like we were talking, all right, in the Cartesian plane, which is where we like to graph stuff. And so I have this angle theta, and I want to draw it in, all right, multiple different quadrants. All right, standard position starts exactly where we would think it starts. We like the positive x-axis as standard position. And almost all angle, unless otherwise specified, will always start with initial side on the positive x-axis, right? Because that's basically the start of quadrant 1, and from then quadrant 1 increases. So if I have theta that lies in quadrant 2, That means I have some angle here. And it goes about that distance. If I have theta in quadrant 4, that means it goes all the way around, all right, with terminal side in quadrant 4. And then we have this word quadrantal. Quadrantal just means it lies on an axis, all right? And if it's not specified, all right, we can pick whatever axis we want. And let's start with the most common one. So if I start right here and I end right here. And this one we should be super familiar with. I know we haven't technically talked about it. We're going to talk about it in like 2 seconds. What do we call an angle that kind of has this, it looks like perpendicular, 90-degree angle. Call it 90-degree or a right angle, right, 90-degree, both those are correct, right? So, okay, so, and that's by far our most common angle, right? That's basically what almost all of trig is based on. All right, so, it's just 2 seconds ahead. All the way around is 360 degrees, AKA 1/360th of a revolution. All the way around the Cartesian plane, starting at standard position, ending at standard position, is 1 revolution or 360 degrees. Now, we should be pretty familiar with degrees, right? And we're going to talk about another measurement that is much, much more common, all right, in trigonometry. But we're going to start with what we're all pretty familiar with. Right angle is 90 degrees and a straight angle is 180 degrees. There's another word for a straight angle, right? If it starts at standard position and ends here, it's a line, right? A straight angle, AKA a line. So let's just get a feel for some angles. So a 45-degree angle. And if we know that's 90 position, if this is 90 degrees all the way up to the start of quadrant 2, then about halfway, or exactly halfway, is 45 degrees. Negative 90 degrees, and so now notice we have the signs associated here. That means we actually have a direction. It's opposite of following the quadrants in order. And 225 degrees. So about where is 225 degrees? In what quadrant? 3, right? And so, I mean, it counts exactly like that, right? We have 0, 90, 180, 270,
360.
Okay, good. Yeah, see? And so it's just counting 90s. All right, and all my pictures look the same, whether it's 60, 30, whatever, all right? The indication of how big that angle is what? How do I know that's 225 degrees, that picture I just drew?
You wrote it down.
Because I wrote the number, all right? Unless you're sitting there with a compass, all right, and a protractor, no one draws the right angle. Label it, all right? We're all about the theory. We're not here in drafting, okay? We're doing the theory that is associated. And then, all right, one more, 405 degrees, which means what's happening on this guy? All the way around. And how far all the way around?
All the way around and halfway.
Halfway? All the way, oops. All the way to over here?
No, halfway through quadrant 1.
Halfway through quadrant 1, right? Because when you take 360 off of 405, what do you get?
45.
45, oh, so it actually looks just like an A, right? Our first angle. And so again, just getting a feel for our angle. So that's all we're doing here. A common notation that you'll see, and actually very, very commonly used in the military, is DMS notation, or degrees, minutes, seconds. All right, now we don't use this notation that much, but we should be familiar because things are presented in lots of different ways. And basically all it does is takes things that are decimals and turns them into integers. Because just like the same concept of people don't like probabilities, but people really like percentages, whole numbers versus decimals. And that's all DMS notation is. It's just a matter of 60 degrees in a minute, all right, and 60 seconds, all right, in 1 minute. So, or I said that backwards, didn't I? 60 minutes in a degree, 60 seconds in a minute. So basically, in order to convert the other way, you're either multiplying, all right, or dividing by 60 or 1/60th, all right, to convert back and forth. But basically, I know just by looking at this value, this is going to be 50 point something degrees. This is going to be 21 degrees and then some minutes and seconds. All right, so it's not changing the number, it's just writing it in another form. Whole numbers versus decimals. So I know this is 50 degrees, and then I have 6 minutes, which then I'm going to divide by 1/60th to turn that into the decimal associated. And I have 21 seconds. All right, and also notice the notation that's used. All right, so they actually they use the slash notation, aka kind of our feet and inches notation, but to actually represent degrees, minutes, seconds. And then 21 seconds, which is actually 1/60th of 1/60th, or 1/3600. But basically, calculate away, all right, and this actually equals 50 point, a number. Degrees. So, all right, it's just about, if you don't like all these decimals, that's why this notation was created. Similarly, I can convert degree notation into DMS. Do the same thing, 21 degrees, and then I take off the decimal and I multiply it by 60. So I took off the decimal, I multiply that by 60. That then becomes 21 degrees plus 15.36 minutes. Since we only want the whole number, I peel off then the 15. So I have 21 degrees, 15 minutes, plus 0.36 multiplied by 60 one more time to get now the seconds. Gives me 21.6 seconds. But again, I only want a whole number. So what do?
Round it,
Round it to,
22.
just make sure we're on the same page. Round it to 22. And so it's just round appropriately. All right, so just another form of notation, all right? And a lot of what we do is converting notation. However, in Trig, all right, we don't really use DMS notation. We don't even really use degrees. Almost every single formula in trigonometry is based on what is known as radians. All right, and a radian, all right, you should understand the fundamental part of this word. Radii or radius comes from what? What shape?
Circle.
Circle. Everything in trig, even though trig's about triangles, it's actually all starts with a circle. So a radian, if I have the radius r, right, on a circle, I take that length r that distance there, all right, same thing. The angle created by this length r on a circle is what's known as 1 radian. This then, all right, from radians is basically how every trigonometric formula is created. And when you have things in radians, the formulas are smooth, all right? When you have anything but radians, they're horrific. So almost everything we're going to be doing is converting DMS notation, degree notation, revolution notation into radians in order to use a formula. Now, unfortunately, again, radians is just not nearly as common, right? Even when we start talking about angles, everyone knows degrees. We know 360 degrees, right? You don't know all the way around. How far is that in radians? Does anyone know? What's 1 revolution? It's actually even a prettier number, 2 pi. Ah, pi is also a number we're pretty familiar with, right? So along those lines, let's start with our very first formula, arc length. All right, for a circle with radius r. All right, if you have, all right, an angle theta, then the arc length, represented as s, is just the radius times that angle, as long as your notation is appropriate. Theta will be in radians, all right, and the radius r can be in anything, all right? Radius, all right, is a distance. Distance is, what's an example of a distance? What are units of a distance? Feet, centimeters, millimeters, miles, all right? Doesn't matter. The big thing is that this angle is measured in radians. And a lot of times we don't get it like that. We get it in DMS notation. We get it in degree notation. We get it in revolution notation. All right. Just to demonstrate the formula though, I started this out with radius r, which is 2 meters. And I actually gave us theta is 0.25. And usually what we write the notation as rads, all right? Rads, all right, indicating radians. Well, that's actually the correct notation, which means the formula is literally plug and chug. One quarter, 0.5. Now, here's the other thing. Everything we put into a formula, we've got to make sure it comes out and is appropriately labeled. So 0.5, what? It's meters still. All right, that's the best part. Because remember that this is length. Length of an arc, length of a distance or arc are the same units. So this still comes out as meters. All right, so the formula can be very, very easy to use, as long as we have things in radians. So along that notation, we need to identify how to convert between degrees, revolutions, and radians. So 1 revolution, right, is 2 pi radians. All right, that's what I just said. That is equivalent to 360 degrees. All right, 1 full revolution, which is 2 pi radians, 360 degrees, all the way around starting position to starting position. Now, the good news is this then we can create equations from that. And it's these little, these notations here are actually all based on this fact, all right? It's basically just a ratio, all right? 1 degree is pi over 180 radians. 1 radian is then 180 over pi. 180 degrees is pi radians, because if 1 revolution is 2 pi, 360, then divide these both by 2, you get pi equals 180. The biggest thing is, whichever direction you're going, multiplying by pi over 180 or 180 over pi, and then just canceling the units, make sure they're appropriate. So if I start in 60 degrees, it's all just dimensional analysis. So if degrees is in the numerator, in order to do dimensional analysis, where do I need the degrees? In the denominator, which means I'm actually using that one. 180 degrees over pi rads, right? Dimensional analysis then says the units cancel. Degrees and degrees cancel, and then I end up with, this is okay, 66/18 pi, 3, pi third rads. And with radians, these numbers often come out very, very nice fractions. Similarly, 150 degrees. And then it's all just a matter of pi over 180, 180 over pi, reduced down. Fractions, fractions, fractions. And we can do this to our heart's content. Now, this last one, all right, so these all came out and reduced down nice, beautiful fractions. Okay, A, B, C, D. All right, for E here, all right, the big thing about radians, all right, is make sure you keep the value exact. And this is the advantage of radians over degrees, right? With degrees, we're always writing things in decimals, which is partially why DMS notation was created. With a decimal, can you ever be exact?
No.
By definition, no. All right, unless that decimal is 0.4, right? I mean, unless it is a decimal that is not infinite. But we know, all right, pi, right? What kind of number is that? There's a word for it. All right, we have whole numbers and integers. Remember what kind of number pi is? It's called an irrational number, right? It goes on forever, right? It goes on forever and it is not exact, which means that we always need a fraction and then associated with pi, and you never want a decimal, all right, with radians whenever possible. The point is that we are exact as possible, right? And that's really what we focus on in trig, is being exact. All right, similarly, I can then convert angles, radians to degrees. All right, if you start in radians, I can then go back to degrees. And it is the same process. I have pi over 6, and if I was doing pi over 180, then this time I'm doing what?
180 over pi.
180 over pi. And notice in a lot of these, oh look, the pi's cancel. And that gives me 30 degrees. And so, as a note, so that's the whole thing, all right? Something that starts out, now 3 radians is kind of a weird one, because you almost never have something 3 radians without a pi involved. But notice that when it comes back to degrees, we do end up, all right, writing degrees with a decimal much more appropriate. right? In radians, you should always have exact values. But degrees, very, very common for us to write degrees with decimals. All right, area of a sector of a circle. So the area of a sector of a circle, and this equation we actually, this is a variation on one that we're pretty familiar with, all right? What's the area, the formula for the area of a circle? Pi r squared. Pi r squared. Right? Of an entire circle, right? Let's write a whole circle, right? The area of a whole circle is pi r squared. This is actually a variation on this. All right, so I still have the r squared, okay? But now this is the sector of a circle. So the sector of a circle is actually a chunk of a circle. In order to do it in this regard, I can do the same thing. I have the area of a circle, and then you multiply this by a fraction, all right? Or let's say if I know the angle of the circle was 360 degrees, or like 30 degrees, so it'd be 30 over 360, right? That fraction of the circle. This is the same thing, but this one, first of all, the angle is always going to be in radians, which is why, all right, there's no pi involved here, all right? And we have the 1/2 here, all right, to account for the adjustment from degrees to radians. But that's all this is. Same equation, all right, same concept, all right, but adjusting that this equation is always in radians, all right? And then once again, r can be measured in whatever. One other note, so fun tangent, all right? You should always remember, all right, the area of a circle, all right, for this joke. All right, so a student is in trig class, and they were learning the area of a circle, and he goes home and he's like really confused, and he asks his dad, he goes, "Dad, I'm like really, really confused. They were talking about the area of a circle and it just didn't make sense to me." And dad goes, "Okay, tell me the formula." And the son says, "They told us the area of a circle is pi r squared." And the dad thinks about it, and he goes, "I don't know what they're teaching you in that class. Pi r round, cornbread r squared." All right, so you should always remember the area of a circle for that joke alone. All right. Okay, so, all right, I want to find the area of a sector of a circle, the angle with 30 degrees. So if I'm told the angle is 30 degrees, in order to use my equation, to practice our equation here, I need to convert this to radians. Once I have, all right, my angle in radians and my radius in whatever, all right, I have, all right, everything in the appropriate units to actually use the formula. Four twos gives me pi 12s. So, and I mean, I could convert this one since we're in area. I could convert it to a decimal, but it's just as easy to, oh wait, hold on. I did it wrong, didn't I? Pi over 3, 2 pi over 3, yeah. You good? Yeah, okay. So pi over 3. And then the units. Feet, almost. Feet squared. Feet squared, area. This actually does bring up one other thing. By definition, these units all have to cancel out. So notice, like, I have radians, and if I actually look at this formula, A equals 1/2, I have feet squared, and then I have rads. So actually, when this comes out, shouldn't I have feet squared times rads? What happens to my radian units? Seems weird, right? We ended up with feet squared and we know area. I was like, you've never said an area that is feet squared times radians. Here's the thing. By definition, a radius is distance divided by the radius. So a unit of radius is always some distance divided by radius. This is always over radius. All right, by definition, a radius is units per radius, which is always what happens to your radian units, just so you know. Now, you can always think of that, or it's just much easier to just think of, I have an area, I had feet, I need feet squared. And that's all I ever do. All right. So the interesting part is what we can do now with this stuff. And the biggest thing that we do, all right, is traveling. All right, distance, all right, dynamic movement versus static movement. Those equations that we were doing, area, all right, and length of a sector of a circle, those are static units. But what happens more often is our dynamic changes, right? What is happening over some time period? Our general one that we should be very, very familiar with, all right, distance traveled, velocity, is s, linear speed, some distance, divided by time. What we're gonna add to that is angular speed. How fast is the angle changing, all right, of an object swept out? Now, the easiest one to think about is spinning a rope. All right, so not only is this object on the end changing, it's going some distance, some rate, all right? It's traveling a distance, but it's also traveling some rate over time. But how fast is this angle changing as I'm spinning this rock on a rope? And that's basically what angular speed is. It's how fast is the angle changing per particular time period. We represent that by notation omega. And once again, notice theta measured in radians, all right? So it's radians per time period, doesn't matter, per second, per minute, per hour. So everything we do is about getting things into the angular speed, all right? So the angular speed, right, is the way of turning an engine, all right? For example, an engine idles at 900 RPMs, all right? Again, a unit we should be familiar with, revolutions per minute. I want to find the angular speed, but I want to find it in something that we're familiar with. By definition, revolutions per minute, that is the angular speed. All right, revolutions per minute, degrees per minute, radians per minute. Those are all appropriate angular speeds. I just want to get us used to converting that to radians. So if I have revolutions, one revolution is how many radians?
Two pi.
2 pi, right? All the way around, all right? That's 2 pi. And again, like I said, this singular fact basically accounts for all three of the most commonly used notations for angular distance. Two pi revs cancel, and then that gives us 1800 pi radians per minute. And that is the angular speed. We were given the angular speed from the beginning. I just want us to get used to looking at stuff in angular speed in terms of radians. What is a much, much more useful fact than actually angular speed is the relationship between linear speed and angular speed. If I take my linear speed equation, all right, which is just arc length divided by time, I put in our very first formula, which was s equals r theta, And then I do some manipulation, really just pulling out the r. Theta over t is the angular speed, which means that I always have a relationship between my linear speed and my angular speed. Especially, right, if you're spinning a rock on a rope, should those be related? Yeah, I should be able to know this and know this. Because the relationship is just a matter of multiplying by the radius, right? Whatever this distance is, that is the relationship. Now, again, this comes back to, this is measured in rads, this is measured in whatever, and then this will correspond to these units and this time period. Now, these formulas are so general that as long as you convert it to radians, all the rest of the units match up, which is a really, really nice fact. Only one thing, all right, a formula where only one thing needs to be in a particular unit is actually pretty rare. Way too often formulas like, oh, this one, I can only take minutes on this one and years on this, and this has to be in this rate and this rate. Right? So these are actually very, very nice general formulas. All right, so exactly what I was talking about. Spinning a rock at the end of a 2-foot rope, AKA radius. At a rate of 180 revolutions per minute. That is then what? Omega, that's angular speed. Also as a note, so I wrote RPMs here because we're super used to seeing that type of notation. Because we do so much dimensional analysis in Trig, get used to writing, all right, revs divided by minutes. Avoid this kind of notation, MPH and things like that at all costs. Because all we do is dimensional analysis. And if you're always writing it as MPH or RPMs or whatever, all right, you're just going to get killed on the dimensional analysis. So write it as unit divided by unit. Okay, so I know immediately I need to convert that revolutions per minute to what?
Miles per hour.
One piece at a time. I haven't even gotten to this piece. Omega needs to be in what units? Radians. Per minute, yeah. I don't have to change the minutes. I mean, I could if I wanted to. We'll leave that for later, okay? But let's just start with, I mean, I could convert it to hours now, but. So that means 1 revolution is 2 pi radians. So this now gives me 360 pi rads per minute. And now I have R and omega, all right, and I'm finding the linear speed when the rock is released, all right, so after we let it go, all right, then how fast will that thing be traveling? I know from my nice handy dandy equation, V equals R omega. And usually when I put these into the equations, I kind of drop the units and I'll just attach the units again at the end. Right? You can keep the units all the way through, but when they're actually going to the formula, I just know what the units are going to be at the end. So what are the units now going to be? I'll help you out. Something over something.
Is it revolutions over minutes?
V is a linear speed. It is minutes, right? I only have one, and that's why I didn't want to change the time period. All right, per minute.
Oh, feet.
Feet per minute. Now, you can put but I always just look back to what my stuff was here. All right, you can put it in here, but it's just one more step you have to write. That's up to you, whatever's helpful to you. And I know it's linear speed, and I know I'm done with revolutions, degrees, and radians at this point, because this is now linear speed. And this is something we're super familiar with, feet per minute. I mean, yeah, we know all about that. And then I look to what the question actually asked. Oh, it says, I actually want miles per hour. So then that's just a matter of, again, dimensional analysis, 720 pi feet per minute. And then I say, okay, some number of feet per 1 mile. Does anyone know it off the top of their head? $52.80, does that look familiar? No? It's always something you can Google. And then, okay, one we should definitely know. Some number of minutes per hour. This one we should know. 60. And then feet cancel, minutes cancel, and right, I have miles per hour. Calculate away. Gives me 25.7 miles per hour. And at this point, I'm converting this to a decimal because I did multiplication and division. I mean, I don't need pi in there anymore, right? We're not nearly as, it's not even standard to have whatever this would be, 5 pi miles per hour. All right. We can then do other things. Because of this relationship between angular speed and linear speed, all right, I can then find relationships, all right, between something like 2 belts or a belt connecting 2 pulleys. So one pulley has radius of 2 inches. Another pulley has a radius of 8 inches. They're connected by a singular belt, right? Basically looks like this. I have a small, here's radius 2 inches. And I have a bigger one, radius of 8 inches. And they're on a system, right? Pulley system. And they're spinning around. Very, very common, simple system. So if the 2-inch pulley, right, is caused to rotate at 3 revolutions per minute. All right, so we're going to call this one R1 equals 2 inches. And we are told then angle 1 equals 3 revolutions per minute. I want to determine the revolutions per minute of the 8-inch pulley. All right, so R2 equals 8 inches. And I'm looking for omega 2. And actually, I'm looking for revs per minute of this. Now, here's the cool thing. The linear speeds of the 2 pulleys are the same, okay? The linear speed. This belt is moving at the same speed, right? It can't be moving different for this belt and this belt. These are moving at different speeds by definition, right? And I mean, we can probably make a pretty good guess, just given these numbers, about what is the angular speed of the big pulley. If the angular speed of that one is 3, right? That one's 2 inches, that one's 8 inches. What do we think this one's gonna be? How many times bigger is this one than this one?
4.
4. So hence, how much slower do you think this one's gonna be?
4 times slower.
Yeah. And I bet that's a pretty good guess. Let's check the math. All right, so first things first, let's convert this to rads to actually be able to use our formula. All right, and we are told, note, V1 equals V2, right? The 2 linear speeds, whatever linear speed we calculate on that one is the same linear speed on this one. So V1 equals R omega, which is 2 times 6 pi, which is 12 pi. And the units there would then be
Inches per minute.
Inches per minute, well done. Then we're, again, back to V1 equals V2. Which means that V2 is 12 pi inches per minute. So V2 equals R2 omega 2. That guy's 12 pi. I'm gonna drop the units just temporarily. That is 8. And for ease of calculation, let's call that X, just so I don't have so many. Which equals 4 over, hold on, up 3. Omega 2, which I've called X, which is rads per minute. Solving that backwards, radians per minute, all the per minute units still match up. And then I wanted to convert that to revolutions. So then one last step. And we do a lot of this. This is what I was talking about with dimensional analysis. People don't like radians, all right? In order to use these formulas, we need to convert it to radians, all right? But a lot of this is converting back and forth, converting back and forth. The formulas are super easy to use. I mean, there's not hard math here, okay? It's just about making sure your context makes the most sense to your observer. All right, so rads cancels, 2 pi, and oh, look. 3/4 revolutions per minute. Looking back, we said that one was 3 revolutions per minute. This pulley is 4 times bigger. We said this would be 4 times slower, AKA 3 divided by 4. So, does our math match up with our logic? Is that good? That's always good news. All right. So don't forget to use a logic check. All right. The math is there, but I was like, we're at the stage where these numbers shouldn't be crazy, disconnected, not understandable values, right? If you got a value that was 500 million, I feel like I did something wrong, right? It's okay. All right. So make sure you use that logic check as you're going through. All right, your calculations. All right, that's good stuff, huh? All right, so that's all the lecture I want to do. So you see, as a note, just a quick note about the activity. So you notice that activity, all right? And so I have these graded problems, all right, which are problems I actually grade via accuracy. Now, I'm going to do my best to give us some time, but as you see, we have like 2 minutes left. All right. Sometimes there's going to be time to work on this stuff, but most of the time these activities are kind of on your own type of thing as well. Do your best. Okay. These ones that are graded, those ones I do look over. All right. Now, pretty much if you do the whole activity, the worst you ever get is a 9 out of 10, and that's like missing almost everything. Okay. The completion problems, then this is additional work at minimum. You should write the solutions next to these answers, but people are always like, oh, I need more practice, I need more practice. Here it is, right? I wrote all these problems, I write the test. These are the most similar to the test problems that you're going to get. The My Math Lab problems, I select those problems, but I didn't write those problems, and so if they're persnickety, that's like life, you know? These problems are definitely the ones you should focus on, all right? And definitely, again, I grade these on these graded problems. I grade on accuracy and completion. I just look, I say, is the writing there? Okay. And like I said, and then the answers are actually here. So if you're solving them and you're not getting the right answer, you know, come ask me, figure it out, try again. But those graded problems I grade on work, so I know just the answers are not enough there. Okay, let's see. So again, well, I do my best to try and have some time. I mean, you know, like, so you saw on this, on the calendar, on 2/6, I have a day where it says chapter 5, part 1 activities. That's just a day where we're gonna be working on activities. All right, so ideally we get through all this lecture. Sometimes we'll have a little bit of time, sometimes we have no time. All right, but that's basically how the class is laid out. All right, any questions? All right, excellent first day. You guys have yourselves a wonderful day. Have fun in, for those who haven't gone to algebra yet, I was like, enjoy your class tonight. I was like, are you in the morning or the night? Okay, so you're about to have algebra. Jacob, are you in the morning or the night algebra?
Night.
The night? Okay, all right, so that means Abel, he was the one in the morning. So yeah, so super fun day of math for you guys. All right. Macy, I was like, you're not gonna take stats? Thought I saw you enrolled in my stats.
I
intro.
did, and then I decided I didn't want to take this and stats at the same time, so.
Wow, that's a good semester. I was like, that's basically what I was talking to them about. It's like double math, double
I,
stats.
I wasn't ready for it, but I think I'll take them in the fall possibly.
All right. I was like, that's a good semester. I was like, math with stats, like,
Yeah.